Today's lesson, we're going to talk about random variable, probability distributions, and how to find expected value using the examples. So the first example we're going to look at it is that the number of heads showing when two coins are tossed. A, gives the probability distributions. B, draw the histogram for the distributions and find the probability that at least one coins come up head. C, find the expected value. So let's look at A. So we're going to have X, random variable X, represent the number of heads. Then we will have, because you're tossing two coins, you could have 0 head, you could have 1 head, or you could have 2 head. If you don't know where those numbers come from, think about the sample space. So what happened when you toss two coins? You can either have 2 tail, the first time tail, second time also getting tail. First time's tail, second time getting head, or first time head or second time getting tail, or both time getting head, right? So that's going to be sample space. So out of this, you have 0 times having a head, you have 1 head 2 times, and you have 2 head, right? So that's the number it comes from. And this one is asking for to graph or draw probability distributions. So I will say probability is distributing for having a number of head for 0 times, 1 time, or 2 times. And that probability is going to be 0 time is going to be only 1 out of 4. 1, having a 1 head is going to be 2 out of 4. You could also use 1/2. And having a 2 head is going to be another 1/4. So when you're adding this number, it should give you total number of sample space. And this is what we call probability distributions. And B is asking histograms. Histogram is the graph, right? So we have the rectangular coordinations, and since we only have either 1/4 or 2/4, right? When 0 head, it's 1/4. 1 head, it will be 2/4. 2 head will be another 1/4. So giving a bar graph like that, this is going to be histogram. And then the other one they want you to do it for part B is find the probability that at least 1 coin. So at least 1 coin means it's okay to have 2 or 3. But in this case, because you're just tossing 2 coins, it will be 2. So it's okay. At least 1 coin means it's okay to be 2 and it's okay to be 1, right? So how do we show that? We will say X had to be greater than equals to 1, right? And finding the probability of that happening is going to be either 1 and 2. So this 3 out of all 4 case, right? So solution of this is going to be 3/4. But how do we find it from here? It's going to be adding 2/4 and 1/4, which is going to be 3/4. Either way, you will end up getting the same solutions, long as if you understand what they're asking. The C, they're asking to find expected value. So if you're looking at the formula right here, expected value is basically multiply this, the case, multiply by probability, plus all the case multiplied by probability, plus case multiplied by probabilities. So here, you only have 3 case, having a 0, which probability is 1/4, plus having a 1, which case probability is 2/4, plus getting a 2, so that's the event, right? And times the probability, so which is 1/4. And this is going to give you, well, this is going to be 0, right? So this is going to be 2/4 plus 2/4. Oops. Let me write it here. 2/4 plus 2/4, which is going to give you 4/4, 1. So this problem, you get expected value of 1. So example 2, we're going to try another finding expected value, but this time for the outcome of the roll of the fair dice. Fair dice, you have 6 dice, right? So let's see. I'm going to find the probability distribution first. So your event is going to be when you roll the fair dice, it will be either getting 1, you can get 2, you can get 3 or 4, 5, and 6. So this is going to be event. What can it happen? It can be 1, 2, 3, 4, 5, 6. And then we wanted to find the probability of that so that we can multiply and then add all this case, right? What's the probability of getting 1? It will be 1 out of 6. All of this is going to be 1 out of 6. Every time you roll, it's 1/6 chance you're going to get these numbers each time. So how do we find expected value of this? It will be 1 times 1/6, right? Plus 2 times 1/6, right? Plus 3 times, multiply by 1/6. 4 times 1/6. Plus 5 times 1/6 plus 6 times 1/6. This will give you, I forgot one case. 0, well, you cannot get 0. So this is going to be it. And when you multiply and add them up, you will get 21/6 in decimal form of 3.5. So your expected value of this example 2 is going to be 3.5. Example 3, again, we're looking for expected value, but this time, number of girls for the family with 3 children. So let me write the sample space. 3 children could have boy, boy, boy. And you can have boy, boy, girl. You could have same thing, 2 boys, but then girl can be in the middle. Or girl can be in front. And you could have 2 girls this time, right? So boy, girl, and girl. Or boy on the second time. Or boy on the last. And then having a 3 girl. So that's the sample space you have, which is 8, total of 8, right? So if we wanted to draw the distributions chart, you have X for the number of the girl. We can have 0 girl, 1 girl, 2 girl, and 3 girl. Probability of getting 0 girl, you have 1, right? Which is 1/8. 1 girl will be 1, 2, 3. So it will be 3/8. 2ger, 1, 2, 3. So will be 3 over 8. And having a 3ger will be another 1 over 8. When you're adding this number, it should be all 8. Just the numerator adding. So expected value of this example, you get it from 0 times 1 over 8 plus 1 times 3 over 8 plus 2 times 3 over 8 plus 3 times 1 over 8, which you end up getting, that cancels out 0. That's 3, 6, 3, so it will be 12 over 8. When you reduce it, it will be 3 over 2, or 1.5 expected value. Okay, example 4. This time we have different types of examples. This one, it say each day, Lynette and Tanisha toss a coins to see who buys the coffee. One toss while the other calls the outcomes. If the person who calls the outcome is correct, the other buys the coffee. Otherwise, the caller pays. Find the Lynette's expected winning. So I need to write the probability distributions and what will be happening. What's the case? So your case is going to be what's going to happen to the coin. And what's going to be called, right? So when you call head, it could be head, right? But when you call tail, it could also be head. When you call head, it comes tail. Or call tail, it could be tail. So this is what it could happen when you're calling. So 2 times matches when calling head, come out head will be winning. When calling tail, and tail is winning. But calling tail, come up head, losing. And call head, but come up tail will be losing, right? So that's going to be, let's write down on the other case. This is caller, win. Head and head will be win, yes. This is not winning. And this is not winning. Only matching wins, right? So we're trying to understand how does this game works and when it's going to be winning. And then we wanted to see if what will be the probability of that. So this is going to be how many outcome you can have. You can have 1, 2, 3, 4 outcomes. So this is out of 4 outcomes, you have 1/4, 1/4, 1/4, 1/4. So expected value of winning is going to be this is winning. Wait, hold on. So this is winning, this case winning, and this case winning. But we cannot use those 2 cases as the value. So what happens when this person is winning? Then gains $1.75 because somebody else is buying it, right? So you gain $1.75. And what's the probability of that? Those two. So it will be 1 over 4 plus 1 over 4, which is 2 over 4. Then what's the other case? Well, if you lose the game, you need to spend that much money. So you're going to spend $1.75. And what's that case? 2 over 4 also, which is half. And so this is going to be when this person winning, and this is not winning. That's why you lose $1.75. I mean, nowadays, coffee is not this price anymore, but it used to be, right? So this, you can tell this is really old problems. And this gives you expected value of 0. What is that expected value 0 means? On an average, for the long run, this is going to be break even. One time, one person win, the other time, the other. So this game is very fair games. And that's what it shows by expected value becoming 0. And let's look at another problem, example 5. Example 5, suppose a local symphony decides to raise money by offering of a microwave oven worth $400, a dinner for 2 worth $80, and 2 books worth $20 each. A total of 2,000 tickets are sold at $1 each. Find the expected value of winning for a person who buy 1 ticket, right? So let's do that. We wanted to see what's going to happen in this raffle. If I buy 1 ticket, there is chance that I can win the microwave oven. Right? That's $400. But I already spent dollars. So actual money that I'll be able to gain is $399. So if I win the microwave oven, I will gain $399. I can also win a dinner for 2, which is worth $80. But I spent $1 already, so it will be $79. For the same reason, I can win $19. And the last, I can lose dollars and not winning anything, right? Let me put the negative outside, losing dollars. And what's the probability of winning a microwave oven? Well, they have only 1 microwave oven out of 2,000 tickets. So 1 person is getting it. 1 person is getting the dinner for 2 out of 2,000 tickets. And two books. So it'll be 2 ticket will be able to get a book worth $20 out of 4,000. And the losing is everything else. So you have 1, 2, 4. Subtract 4 from 2,000. You will have 1,996 out of 2,000 probabilities. So in order to find the expected value of that problems, we do 399 times 1 over 2,000 plus 79 times 1 over 2,000 plus 19 times 2 over 2,000 plus negative 1 times 1996 over 2,000. And when you plug in all those numbers, look like I will get negative 0.74. Having expected value negative, this means that you're going to lose. You're going to lose this much amounts if you play this game over and over again, let's say 50 times, 100 times. You're expected of losing 74 cents is your expected value. So in other words, you're going to lose anyway, so why playing, right? Okay, I'm going to do one more problem, and this is involving insurance company. So here it said, suppose that at age 50, you receive a letter from the mutual insurance company. According to the letter, you must tell the company immediately which of the following two options you will choose. The first options, take $50,000 at age 60 if you're alive and $0 otherwise. Or take $65,000 at age 70 if you're alive and $0 otherwise. Based only on the idea of expected value, which should you choose? So not just picking what you like to pick, but you wanted to use the expected value to decide which one. So how we're going to find expected value? Here the company already gave you probably distribution for person living. So the age of 50 and 60, person living probability is 88% because you have 0.88 probabilities. It means 88%, right? And people who living between 50 to 70 is 64%, which is 0.64 probabilities. So in order to find the expected value of the first options, expected value of first option is going to be first option is going to be getting $50,000 when you're alive. That's your probability, so you multiply that. Or you get zero amount, and your probability of not alive is going to be 0.12. Why? Because it's 1 minus 0.88, right? And this is going to give you around 44,000. What about the expected value of the second options? Second options, you get $65,000, but your probability of alive at that age is going to be 0.64. Otherwise, you get zero amounts, and your probability is going to be 1 minus 0.64. So it will be 0.36. This will give you 41,600. So since you get more money, just comparing as the expected value, the best option will be the first options. And if you wanted to go over example 6, we have the class notes will show you how to do example 7 also. So this is how you're going to find expected value from these sections.